Hello out there. Welcome back to another lesson in AP Calculus AB. We are in Unit 8. Unit 8 is more on integration. We've looked at some additional formulas, and we went back and we revisited both the mean value theorem, and we picked up the rest of the fundamental theorem of calculus. This lesson is called Functions Defined by Integrals, and we are going to be using our fundamental theorem of calculus in an interesting way. We're going to be looking at functions that have integrals in them and be applying our understanding of integration as area under the curve, as well as our understanding of the first part of the fundamental theorem of calculus that we learned in the previous lesson. So, without further ado, let's get to it. Okay, the graph of f consists of a quarter circle and line segments. Let g be the function given by g of x equals -1 plus the integral from 0 to x of f of t dt. All right, first we need to find g of 0. Okay, so to find g of 0, we'll simply just use g of x. So g of 0 is equal to -1 plus the integral from 0 to 0 of f of t dt. Well, we know what that is because the integral from 0 to 0 is simply 0. Any integral from a number a to a is an area of 0. So this is just -1. Next, we'll find g of -1. Well, that's -1 plus the integral from 0 to -1 of f of t dt. Now, we need to be careful because 0 to -1 is actually moving backwards. So from 0 to -1, we have this triangular area here that has an area of 1, because 1/2 base of 1 times height of 2. So that's an area of 1. But we're going backwards, so that's a -1, making this value -2. Okay, for g of 2, we'll be doing -1 plus the integral from 0 to 2, which is pi r squared. And r is a radius of 2, but we're only doing 1/4 of it. So that's just pi. Next, we'll do g of 5. Well, g of 5, we can use our value from g of 2, which was -1 plus pi. Plus, we need all this area here. Well, this is 1, 2. And then this here makes 3 between these two, and this makes 4. So we have 1, 2, 3, 4. So this is a -1 plus pi minus 4, or -5 plus pi. Okay, let's take a look. On what intervals is the graph of g increasing? Okay, so if we want to know when g is increasing, we need to know the derivative of g. So the derivative of g, or g prime of x, is equal to the derivative of this. Well, the derivative we can take in separate this over addition. So I'll do the first part, the derivative of -1, a constant is just 0. But then I have to do the derivative from 0 of the integral from 0 to x of f of t dt. Well, that is f of x by the fundamental theorem of calculus part 1. So we know that this graph here is g prime of x. And since this graph is above the x-axis from -1 to 2, we know that g is increasing there. So g is increasing on the interval from -1 to 2 because g prime of x is greater than 0 on that interval. We can think about it in terms of slopes because we know that if the derivative is above the x-axis, the slope is positive. And if the slope is positive, then the graph is going up. But also we can see it in terms of area. And as these areas are above the x-axis, this accumulation is growing, as opposed to here where the area is negative. Okay, we're going to find all the values of x on -1 to 5 at which g has a relative maximum. So again, we know that g prime of x is equal to f of x. So we need to use this graph to find when g has a relative maximum. Well, g is going to have a relative max right here because g prime changed from positive to negative, g changed from increasing to decreasing. So we're going to say at Actually, let me say this differently. G has a relative max at x equals 2. Now, they just asked for the x values, but note we could have found the y value as well, since we actually already found the y value, being, I think it was like negative 1 plus pi. But G has a relative max at x equals 2 because G prime of x changes from positive to negative there. Find the absolute minimum on negative 1 to 5 and the value at which it occurs. Well, from negative 1 to 5, we actually evaluated several points. The critical points, though, are here, here, and the endpoint over here. So we just need to check those 3 points. We need to find G of negative 1, which I believe was a negative 2. G of 2, which I believe was negative 1 plus pi. And G of 5. What was G of 5? Negative 5 plus pi. So which one of these is smallest? Well, let's see here. Pi is about a little bit more than 3. So this number here must be something not as small as negative 2. So the absolute minimum of G is negative 2, and that occurs at x equals negative 1. And we found that by the candidates test. Okay? On what intervals is the graph of G concave up? Well, we need to look at the derivative and see when the derivative is increasing. That's from negative 1 to 0 and from 3 to 5. Because G prime of x is increasing. Okay, F now. At which x coordinate does G have a point of inflection? Well, that's simply where we change, G prime changes from increasing to decreasing. So that's going to occur at x equals 0 and at x equals 3, it looks like. So at x equals 0 and x equals 3, because G prime changes from increasing to decreasing or decreasing to increasing. All right, let's take a look at another example, this time one more equation-based. So given that f of x is equal to the integral from negative 1 to x of t of plus 2 times t minus 3 squared dt, for what value of x is f decreasing? Explain. Okay, so if we're going to find when f is decreasing, we'll need the derivative of f, so let's do that. All right, we want to be real careful that we make sure this is just an x here before we apply the fundamental theorem. Because if this is like some function of x, we have to multiply by its chain. But this one's just an x, so I'm going to say x plus 2 and x minus 3. That's the fundamental theorem of calculus that tells me that if I take the derivative of this integral expression, it just replaces the t with x. Now, immediately, I'm very suspicious of this x minus 3 factor because it's squared. And usually, polynomials will bounce whenever you have a squared factor like that. Well, I say usually, I mean always, if it's an even power. But let's go ahead and do a number line so we can see that. Negative 2 and positive 3 are the places where f prime is 0. If I plug in 0 for x, I would get a positive times, well, this is a positive, right? Because it's always positive, except for at 3 when it's 0. So a positive times a positive, positive. If I plug in 4, well, 4 plus 2 is positive, and again, this is always positive. Not until I get over here to like negative 3 would this stay negative. So there we go. For what values of f is x is f decreasing? F is decreasing on the interval from negative infinity to negative 2 because f prime of x is less than 0 there. And that's all there is to it. All right, let's try the next one. Suppose that 3x squared minus 12 equals the integral from c to x of f of t dt. Oh yes, this is an interesting problem. What is f of x? Okay, so we need to find out what f of x is. And the way I'm going to do that is I'm going to remember that if I take the derivative of this right-hand side, that will give me f of x. So I'm going to actually apply the derivative to both sides. So this derivative becomes 6x, and this derivative here becomes f of x. So f of x must equal 6x. Now let's find the value of c. Well, I know that the integral from c to x of 6x dx is equal to 3x squared minus 12. So when I integrate 6x, I get 3x squared, and we'll be evaluating that from c to x, which becomes, well, I should be more careful with my notation. This is why I use t. This is 6t dt. Don't want to have x here and there. All right, that makes more sense. Now I'm plugging in x, and I get 3x squared minus 3c squared. Well, that's supposed to equal 3x squared minus 12. So these get canceled out, and I can see that at negative 3, c squared is negative 12. So c squared is equal to 4. So I get that c is equal to plus or minus 2. So apparently c could be positive 2 or negative 2, and we would still get the same value. And that's because of that squared feature there. All right, I've got some practice problems for you to do. I got practice 5.1 and 5.2. Let's start with both of those right now. Pause the video and give them a try. All right, let's see how we did. The integral from negative 2 to 5 of f of x dx equals 4. We want to find the integral from negative 2 to 5 of 3f of x minus 2. So we need to use our properties of integration. And I will split this apart. And remember to apply the dx to both terms there. Oh, I already did the negative, so I don't need the negative inside. Okay, I can pull the 3 out. So this is 3 times the integral from negative 2 to 5 of f of x dx minus the integral from negative 2 to 5 of 2. Well, you can do the math if you want. You can integrate, take that 2x and evaluate from negative 2 to 5. But I prefer to just think about this as a rectangle, because that's y equals 2 as a horizontal line. And we're looking at a bounds from negative 2 to 5. So that's 7 on the base, 2 on the height. So that's just a 14. So this is 3 times, they gave me that value is 4 minus 14 is a negative 2. All right, let's take a look at the next one. Find the intervals where f is concave down. So to find when f is concave down given an equation, I need the second derivative of f. So I'll take the first derivative. The derivative of 10 is 0, and then I have to use the fundamental theorem of calculus, which tells me I just replace those t's with x's. Then I need the second derivative to see concavity, so I say 3x squared minus 2x minus 5. And this I set equal to 0, and I can actually factor this one, it looks like. So we're going to say 3x, we'll say minus 5x and plus 1. So that would give me a plus 3x minus 5x, so it's a negative 2x. So on a number line, the zeros of this are at negative 1 and positive 5/3. If I plug in 0 into this f double prime, I do get a negative number. If I plug in a number bigger than 5/3, say like 10, 30 minus 5 times 10 plus 1, it's clearly 2 positive numbers. If I plug in a number less than negative 1, like negative 2, I would get a negative number here clearly, and also a negative number here, and 2 negatives multiplied to a positive. So when are we concave down? F is concave down on the interval from negative 1 to 5/3. Why? Because f double prime of x is negative. All right, let's do the next one. Evaluate each of the following. So work this practice problem on your own. Pause the video, please. All right, let's see how we did. Taking the derivative of the natural log of x squared minus 2x plus 1. That's just u prime over u, y'all. 2x minus 2 over x squared minus 2x plus 1. On the next one, we have the derivative with respect to x of 4 to x. This one requires the fundamental theorem of calculus, so we'll be replacing the t with x, making this secant of x squared. All right, on the next one, we have the derivative from x to 9 of sine of t squared. So remember that this is actually inside out. This is backwards because the x is on the bottom. So this ends up becoming a negative sine of x squared. And here we get to use our chain rule version. So this equals the natural log of t gets replaced with e to the x. But then we have to multiply by the derivative of e to the x, which is e to the x. And this is interesting because we could actually simplify this as something kind of neat. The natural log of e will cancel out, giving me just x times e to the x. Okay, let's get going. Let's keep going. All right, practice 5.4. We've got f and g, and I'd like you to find the limit as x approaches 3 of f over g. Pause the video and give it a try. All right, so first we're going to try direct substitution. But the integral from 3 to 3 of t squared minus 1, well, that is equal to 0 because I'm integrating from a number to itself. And clearly, g of 3 is also 0. So what I need to say is that the limit as x approaches 3 of f of x, that's 0. And the limit as x approaches 3 of g of x is also 0. So therefore, by L'Hopital's rule, we know that the limit as x approaches 3 of f of x over g of x is actually equal to the limit, if it exists, as x approaches 3 of f prime of x over g prime of x. Now, the derivative of f of x requires us to use the fundamental theorem of calculus, so I just replace the t with x, and I get x squared minus 1. The bottom, the derivative of g, though, is just a 1. Got to write limit every time. Then I plug in my limit value 3, and I get 9 minus 1 is 8. All right. And I think that's it for this lesson, so study hard, and I'll see you in the next one.